All right. So welcome to the TIFR-CAM Colloquium. Today we have Koushik Ramachandran, our own from TIFR-CAM, and he'll be telling us about critical points of the landscape function. So over to you, Koushik.
Thanks. Thanks, Nishant. And I'm very happy that Colloquium is held regularly. So chance for everyone to get to know what others are doing within our center and also from outside. Okay, so here is the outline of my talk. I will introduce the problem, give some examples. Then I'll give you motivation. Why am I considering this problem and what motivates the study of these things? A few known results, so history of such problems, and then I'll present our own results. So by the way, this talk is a joint work with Erik Lundberg, who is in Florida Atlantic University. And I'll finally end with, after presenting, so the talk will be light on the proofs. I won't really give any detailed proofs, maybe just a sketch of one thing. And finally, I'll end with some conjectures and open problems. So let's get started. So I will only deal with domains in R2 and so in the plane. Okay. So what is the main object of our talk? So this is, so let's take a domain, bounded domain, finitely connected. So that means it's okay to have a few holes in it. For the purpose of this talk, you can imagine that the boundary of the domain is very nice, say smooth all the time. And let's define this function. It's a well-known function. It's called landscape function of omega. What is it? It's a function which satisfies Laplacian of this function v is -2 in the domain. So it's constant, it's -2, and v is 0 on the boundary. Okay. And in the older literature, this is called as a torsion function. So this is torsion, where except that this you might change the boundary conditions, so you can have v equal to c1 on each component. So that is called torsion function, but we stick to this. Okay. So what's important here is that the Laplacian is a constant. This -2 is a particular normalization that we choose. That's it. Okay. And the main point of this talk is to look at the set of critical points, which is where the gradient vanishes for this function v. And we ask, what is the size of this set of critical points? How big is it? And how does it depend on features of your domain omega? So that is, can you give, suppose the domain looks a certain shape or domain has certain number of holes, then what can you say about the set of critical points and its size? Is this okay? So this is a very simple.
So yeah. Koushik,
yes.
By finitely connected, you just mean finitely many holes. You mentioned this, but I just wanted to clarify.
Yes,
so
finitely many holes. Yes. So a simply connected domain, no holes would mean k equal to 1. Connectivity constant is 1, and one hole would mean doubly connected. So annulus will be connectivity 2. Yeah.
Okay.
Yeah.
Thanks.
So yeah, and feel free to interrupt me with any questions if something is not clear. Okay, so this is our main problem. You look at Laplacian v is -2 and 0 boundary conditions, and you ask for the size of the critical points. And yeah, so now let me give a few examples. One should always look at some examples. So suppose omega is a disk. Okay, then in this case, actually, you can write down explicitly what is the landscape function. So let's, for simplicity, let's just look at unit disk. Maybe I reduce the size of, yeah. So let's say this is the unit disk of size 1. And so then I can simply write v of z. So by the way, so if you go back to the definition, so if at all you have a solution v which satisfies this, there is only one. Okay, because if there are two, v1 and v2, then the difference Laplacian of v1 minus v2 is 0. because both have constant Laplacian. So if there are two of them, if you subtract, it will be 0. So in particular, this will mean the difference is harmonic and both of them vanish on the boundary. So by maximum principle, V1 should be equal to V2. Okay, so you can always talk about the landscape function of a domain omega. So if you find one, that's it. So let's look at the unit disk. And if you look at V of Z is 1 minus mod Z square by 2, you see that mod Z equal to 1 on the boundary. So it vanishes. And if you take the Laplacian, Z square mod Z square is X square plus Y square. So you can actually compute it and it turns out to be minus 2. So this is the landscape function for the disk. And if you take gradient of V is exactly minus Z, right? X squared plus Y squared times minus half. So if you take Vx, Vy, it's negative of X comma Y. So there is exactly 1, 0. So where it is 0 is exactly origin. So there is only one critical point. Okay. And so that's a basic example to keep in mind. Let's look at another example. It is possible that you might have infinitely many critical points. So if you are an annulus, so let's draw another picture. Let's draw the circle of radius half and circle of radius 1. Okay, and let's look at this annulus. Then remember again, we want this and V equal to 0 on the boundary. This is on omega. Then you see that you can always, so actually you can find a radial solution here. Okay, so you can find a radial solution. If you find a radial solution, so then just look at V as a function of the radius f of r. Then you see that f prime of r, it will vanish. So first of all, why is there a critical point always? So let's go back. I didn't really mention it. Why is there is always at least one critical point? Because you see that we will attain a maximum somewhere inside, right? So Laplacian V is negative. It means that V is a superharmonic function, which is 0 on the boundary. So by minimum principle, okay, there will be a critical point. It has to attain maximum somewhere. So this will be a critical point. This will be in the interior. So there is at least one. We are showing that in a disk, there is exactly one. And in an annulus, because the solution is radial, you will have at some point where f prime vanishes, actually there is a whole circle. So it's not just the critical set of critical points. There is a whole circle of them for an annulus. Okay. So you can have infinitely many, then it's not so interesting to say, okay, what else to say about this? Nothing else. Okay, so that those are initial two examples to keep in mind. So let's talk about a few observations which are useful. So as I mentioned, always there is at least one critical point because maximum has to be there. And any critical point, in fact, can only be either a saddle point or a maxima of V, right? Because Laplacian is negative. So you can't have, by the minimum principle, there are no minima inside. There is only saddles and maxima. And near the boundary, this is an important observation. Near the boundary, gradient V does not vanish. This is something in PD is called the Hopf lemma. And okay, so how to think about this? Okay, there are some students I saw that first year students also are attending. So, I mean, just to give some analogy, so I said Laplacian V is minus 2, right? And V is 0. I mean, think of the one-dimensional case. Suppose you are in R, okay? What would be the analog of this? F double prime is minus 2 on some interval or whatever, and F is 0 on the endpoints. So this is, if you draw this guy, it will be like a parabola, right? F double prime is minus 2. So it is like a parabola, which is 0. So it will be like an inverted parabola AB. And so that means, so gradient cannot vanish near the endpoints, right? The derivative will not vanish near the endpoints. So it is sort of an analogy of this, but it's not, the proof is not like this. It's not a very trivial fact, this Hopf lemma. So if you have not seen it, maybe you can just keep this analogy in mind and move ahead. So in particular, this means that since a gradient does not vanish near the boundary of the domain, that means all the gradient, if at all there are critical points, all of them have to lie on some compact subset of omega. Is that okay? And so you might be tempted, okay, so we have the disk, we wrote down explicit formula, there is an annulus, maybe we do radial solutions, write down the PDE and then solve it explicitly, but only in some domains you can write down an explicit formula. Ellipse is a good exercise. It follows actually. So if you have an ellipse, so let's say if you have x squared by a squared, y squared by b squared less than 1, then you can actually write it down explicitly. It's a multiple of this function, 1 minus x squared by a squared, 1 minus constant times x squared by a squared plus y squared by b squared. Okay, yeah. And there is a domain later on I will introduce called the Neumann's Oval, which is very famous in approximation theory. So that one also there is an explicit formula for this, but in general it's not available. So how does one get a handle on the set of critical points? So okay, so let me mention one thing. This is, as I said, yeah.
Koushik?
Yeah.
Shiva has a question.
Yes.
Is this true? Is this all true in R2, or is complex plane actually used in the arguments?
Where? Sorry, I didn't get the question. So let me look at the chat. No, R2. Yeah, R2. Yeah. I mean, it's the same. I identify everything with. Yeah. Oh, you mean in Rn or? Yeah. So in Rn, it's not. In Rn again. There will always be a critical point. The solution, but even in nice domains, you can have infinitely many critical points in Rn. In n bigger than equal to 3. So we will see in a matter of few minutes that if you are in R2 and a simply connected domain, then there are only finitely many critical points. You can't have infinitely many. Yeah. Oh, okay. Yeah. So as I said, sometimes this landscape function is also known as torsion function, and there are some probabilists. So just to give connections to what this is in terms of probability, this landscape function V, if you write V of Z, this is actually exactly same as Ez of tau. So what you have is you have some domain like this. Okay, so what you do is you are at Z. You start Brownian motion at Z and you wait for the first time until it hits the boundary. Okay, so it will go somewhere and it will hit the boundary. Tau is the time, exit time for this time taken to hit the boundary. And so V of Z is exactly the expected time. Start at Z, expected time to hit the boundary is actually the landscape function. So there are some connections with probability. Okay. Okay, so we have established that there is at least one point, critical point. There can be infinitely many, like in the case of an annulus. And if at all there are critical points, all of them have to be on some compact subset. Okay, so let me give you some motivation. There are, of course, this is just study of critical points. It has a very long history, but our primary motivation came from something called the localization of eigenfunctions. So I will just briefly tell you, this won't be rigorous, but I will tell you this problem and how it relates to our problem about critical points. Okay, so so let's look at the Laplacian very famous problem. So look at the eigenfunction eigenvalue problem for the Laplacian in a domain. So you have minus Laplacian u is lambda u and u is 0 on the boundary. Okay, so this is the eigenvalue problem for Laplacian, and it's a well-known fact that there are infinitely many eigenvalues. Lambda 1 positive, there it's simple, and then you have lambda 2, lambda 3, and so on, and you have corresponding eigenfunctions u1, u2. So whenever I say low energy eigenfunctions, I mean the ones which correspond to the lower eigenvalues. So lambda 1 is a phi 1. Let's say phi 1 is an eigenfunction corresponding to lambda 1. I call phi 1 like low energy. So high energy are the ones that go off to infinity ones. So lambda n very large, those are high energy. Small n I refer to as low energy eigenfunctions. And what is observed? So physicists have know way more about this than us mathematicians. But what we observe is that in some domains, these low energy eigenfunctions, they exhibit localization. Okay, what does it mean? So in a very crude sense, localization in this way means that you are the eigenfunctions are concentrated in a small region and they are negligible everywhere else. Okay, so of course remember that this suppose phi is an eigenfunction. So phi is one can show that phi is real analytic. So you cannot hope that phi vanishes, that it is supported on some. So if you have a domain, it's not that eigenfunction is concentrated, its support is on some compact subset and everywhere else it's zero. That cannot happen because phi is real analytic. So what we mean is that most of it is in a small region, everywhere else it's negligible. Okay, so this is observed. This is not, we are still trying to understand why it happens, in which domain it happens, and so on. So for instance, this localization will not happen in a square. Suppose you take a square, then you know exactly what are all the eigenfunctions. They are sin x and sin nx, sin ny. For instance, suppose you take the square to be 0 pi cross 0 pi, then it's sin nx and sin times sin ny. You see that actually they are well spaced, equally spaced. Okay, and so just to give a nice example, this I took from this paper of Grebenkov and I don't know how to pronounce. I think probably Neumann, maybe. I don't know. So you take a nice polygonal domain, okay, and it's called a bottleneck. Of course, it's essentially two rectangles connected by a thin channel, and you see that this is plotted, the 19th eigen mode. This one is more or less living on the right hand side, the right rectangle. Okay, and it's not so I mean it's not zero, but it's very small on the other one. Okay, so you won't get, if the domain has very nice symmetry, then localization may not happen. Okay, so think in the terms of the disk or the square or things like this, it won't happen. But if you even nice shapes, even for polygons with some thin channel or fractal like domains, you will notice localization. So we are interested in the question, where does it localize? Suppose I give you a domain like this, is it possible to predict here is where it will localize? So that is one thing. And let me give you another way one can talk about localization of eigenfunctions. So let's take a slightly more complicated operator, not that much more complicated. What I do is I took initially just the eigenfunction of Laplacian, right, minus Laplacian. Now I add a potential. This V is a potential. That means just a positive bounded function, let's say. And one can define, similar to Laplacian, one can define what is the landscape function for this operator L. So we define it as that solution to LV equal to 2 in omega with zero boundary conditions on the with zero boundary conditions. Okay, so we look at a more general perturbation of the Laplacian like this, and we ask for the same thing. So you can look at the eigenfunctions of this, and we ask for what kind of domains, that is, what kind of shapes. We said square will not exhibit localization, but what kind of domain or what kind of V. So you can start with, now perhaps you can start with a square, okay, and make your V very complicated. You look at this operator L on a square. What kind of V will do you have to take so that eigenfunctions of L exhibit localization? And we want to understand, where does localization happen? Where are the localization spots? And another question which is of great importance in applications is you start with a domain. Let's say localization happens for the eigenfunction. Suppose you just perturb the domain a little bit. Do you expect that localization spots are also perturbed just a little? Okay, so the answer is in general no. So there are very many things in you can even watch on YouTube that especially when you're talking about sometimes these are nonlinear problems, they're not the ones directly connected to this, but okay, just to keep in mind that generally no, it won't be perturbed a little bit. Okay. Okay, so what's the connection to our problem with all this localization? It is this landmark paper by a bunch of very famous mathematicians, Arnold, Guy David, Marcel Filochet, David Jerison, and finally my advisor, Svetlana Meboroda. So what they showed is, so they looked at this kind of operator, this L is minus Laplacian plus V, let's say on a square or something. Then they showed that remember, you look at low energy eigenfunction U lambda, they showed that U lambda, where is it localized? It is localized essentially on the set where the landscape function, remember, landscape function is the solution to LV equal to 2 in omega and V is 0 in that boundary. So it's like saying that the eigenfunctions, those are a little bit complicated, but if you want to know where it's localized, it's a remarkable theorem that it is controlled by the behavior of this landscape function. So V predicts where U lambda is localized, and this is the reason. So in particular, suppose you want to know where are the localization spots, then to start with, we can look near the maxima of V. Wherever V attains a maxima, then we know that at least some of the eigenfunctions will be localized there, right? Because V is bigger than something, so definitely V equal to maxima, then that will be a spot where localization probably happens. So this was our main motivation. Just a toy model, how to understand where localization happens and where are the critical points. Okay.
Koushik?
Yes.
Can you say a little more? So you said that by localization, you mean that the eigenvalues have very small values outside these domains. So I'm assuming the domains where Vz is less than 1 over lambda plus delta, it will be very small. But I'm guessing that this was a more quantitative theorem.
Right.
Can you say anything to this regard? Or?
Yeah, it is more quantitative. Yeah. So yeah, it's a bit more technical than that. I didn't want to
All right, that's
give
fine.
the main
that's
thing
fine.
because it's,
sure.
yeah.
All right.
Yeah, you have to quantify how small is small, and so things like that. But I don't want to get into those kind of issues here. Just want to say that in some regions it is big, and other regions it is small, without quantifying this.
Sure,
Okay?
this is fine for now. Yeah.
Okay, so yeah, because landscape function controls where the eigenfunctions localize. This is one of the main motivations for us to study where are the critical points in particular, right? So, and since maxima are coming under the critical points, so in particular, if we study where the maxima will occur or predict where the maxima will occur, then okay. So this is taken from the paper of Philoche and Meboroda. I mean, it's a very interesting, groundbreaking work going on called she's running a program called Anderson localization and localization of waves. But anyway, so this is a picture of, so what they have done is they have taken a square. So let me just briefly tell you what they have done. You take a square and you break it into some number of subsquares, a large number, let's say 100,000 or whatever. And what you do is you take V is chosen to be constant on each square, piecewise constant. And the way that they choose, V is a uniform random variable on some whatever, I don't know what they took, maybe minus positive, right? Okay, yeah. So V is from uniform on 0 to some large number. So this is a uniform random variable. So you take this random potential and then you look at where are the localizations happening, and they can actually predict. So numerically, they look at this landscape function. They can actually predict. You see the rightmost picture, the first 5 eigenfunctions. They are somehow captured within what they call the potential wells of these landscape function. V is capital V. So yeah, so this is the potential. Okay, so yeah, again, yeah, I'm sorry that I'm not explaining this maybe very clearly. So we have this operator L equal to minus delta plus V, capital V, and suppose you choose V to be random potential with you divide into subsquares. On each square, you choose it to be some random number, say uniformly. Okay. And now you look at the eigenfunctions. Where are they localized? It will be random, right? And but somehow they say, they prove in these series of papers that there is a universal function, this landscape function, which predicts where they are likely to localize. Okay. And just to tell you that this is not just some mathematical or something, here is very cool. And this picture is taken from a place in France, on a highway in France, where it's an acoustic barrier. Okay. And it's a very complicated shape. You see that it's a repeating pattern, it's like a fractal pattern. So this is a noise absorbing wall on a highway. Okay. And this was done by, this design is patented by two professors, physics professors at École Polytechnique, Bernard Sapowell and Marcel Filochet. So if imagine, so whenever noise hits the wall, it will vibrate, right? So it is like an eigenfunction, but you want to make sure that they are localized in smaller and smaller spots. That's the point of noise absorption, right? So they came up with this shape where somehow these the localization is captured in smaller and smaller spots. So this is for real. So you see here none better, a very amazing application of these localization phenomena, and real application to whatever we are talking about. Okay, so so let me tell you now a few known results, the history of this. As I mentioned, you can have a set of critical points for this landscape function. It can be infinity, but if it is infinity, there is a very nice structure theorem that if at all there are infinitely many critical points, then it has to be essentially finitely many analytic loops. That means that, yeah, so it can either be, you can't have it in a simply connected domain, but yeah, so you see in an annular region, it is like, so critical set of critical points was an actual circle. Otherwise, in general, it could be finitely many analytic loops and maybe a few isolated points. Okay, so this is the structure theorem for this. It's actually a very neat theorem, something that is understandable to someone who has taken a first course in PD. Okay, so I won't do this now, but it's a good exercise, that if at all there are infinitely many critical points, show that it's the union of finitely many analytic loops and few isolated points. Okay, so, and in particular, so if your domain is simply connected, then the set of critical points, there cannot be infinitely many of them, right? So let me draw this. Why can there be, based on this structure theorem, here is a simply connected domain. Why can't there be infinitely many? See, by the structure theorem, if there are infinitely many, there should be a loop like this, right? So on this loop, just on the boundary of this, all the gradient of V should vanish, right? How can it happen? Because if gradient is vanishing, that means, so here Vx should be 0, Vy should be 0, right? But remember, Laplacian V is -2. So in particular, if you take Vx and Vy are harmonic, right? If you take you differentiate this once. If you take Laplacian of Vx, you see that it will be 0. Okay, so Vx and Vy are harmonic. If you have an actual analytic loop in a simply connected domain where they are both vanishing, that means V should be identically 0, because these are harmonic function. Sorry, Vx is 0, but Vx is harmonic. So Vx is 0 identically inside this region, but Vx is 0 identically means V is constant, but V cannot be constant because Laplacian V is -2. Okay, so in a simply connected domain, you cannot have these loop. That means you only have isolated points, and remember that they are all sitting in a compact set. So there are only finitely many isolated, finitely many points for the critical set. Okay, and now we come to the topological parts of the result. So as we said earlier, the critical points fall under two categories. Either they are saddle points or they are maxima. Okay, and a theorem of Alessandrini and Magnanini, it says that suppose you know that the landscape function has only isolated critical points, then there is a relation between the number of saddles and number of maxima. What is it? Then S minus M. S is the number of saddles, capital M is the number of maxima, K is the connectivity, that is number of holes plus 1. So just to keep in mind that if you are an annulus, K is 2. And simply connected means K is 1. Okay. So S minus M is K minus 2. This is a topological theorem. The only way I can explain this in a sort of a fake proof. It's not the exact same thing, but suppose you look at gradient V. Okay, this is non-zero as we observed. So it's a non-vanishing vector field on the boundary of omega. And now you apply this famous theorem of Poincaré-Hopf. Okay, so for students who have seen some complex analysis, this is very crudely, it is like some winding number argument. So you have a gradient every time you go around a critical point, depending on whether it's a saddle or maxima, you have to associate an index with it, plus 1, minus 1, so on. So it is sort of like a winding number argument. But beyond that, I am also not an expert on this topological stuff. So I will just leave it at this. So if you know there are isolated points, isolated critical points, you know a relation between number of saddles and number of maxima. This is the content of this. Okay. All right. So yeah.
Venki has a question.
Yes.
So this topological theorem is a two-dimensional result, is it?
Yeah, in this case, no. Poincaré-Hopf is not. It's not just a two-dimensional thing. Yeah. So this one, I think. Yeah. So in higher dimensions, I don't think that even in very nice domains, you can have infinitely many. But if there are only finitely many, yeah, I don't think there is anything that will. Yeah, if you know that they're isolated, I don't see any. I don't see any difference between applying. I think the proof is the same. Yeah, I mean this is just this is not anything to do with particular structure of. There is nothing about R2 here. If you know they're isolated, you can do the same argument. Yeah.
Okay.
Okay.
Thanks.
Yeah. Okay, so now we have seen that if it's simply connected, there are only finitely many. Now there is a geometric part of the theorem that if you are convex, if the domain to start with is a bounded convex domain, then there is only one critical point. So just recast your memory back to the initial example we did. This was the unit disk, and we did look at this 1 minus mod z squared by 2 function. This was your landscape function V. We saw that gradient was vanishing only at the origin. So this is the only critical point. So this is a generalization of this. It's a very beautiful theorem due to Machar and Limanov. It says that on convex domains, there is exactly one critical point. And how to show this? Okay. As I said, it's highly non-trivial. This is not at all trivial. But first, you have to show that the number of maxima is exactly 1. Okay, and this depends on an argument which uses convexity of the level sets of this landscape function. Suppose you know, so remember the topological theorem. So let me just recall this here. Topological theorem, which said that S minus M, the number of saddles minus number of maxima, is connectivity minus 2. Okay, suppose you take a convex domain. In particular, it's simply connected. That means K is 1, right? So S minus M, 1 minus 2, which is negative 1. Okay. Suppose I can show that M is 1. Then S minus 1 is minus 1. So S is 0. So there are no saddles. So there are no saddles. There's exactly one maxima. So number of critical points is 1. Okay. So if you show M is 1, then the topological theorem kicks in and shows that saddles, there are none. And let me just tell one word about how one shows this M is 1. It's a very neat argument. So it depends on this fact that convexity of level sets, which is that you take the landscape function, you show that you take any positive constant C, V bigger than equal to C, this is convex. So that means if you start with a convex domain, then the solution to that PDE inherits the convexity properties. So the level sets inherit property of the domain. This is a very general feature of many elliptic PDEs. Lot of properties of the domain are inherited by the solutions. Okay, so you show that V bigger than equal to C is convex for every so for all C positive. Okay, and then the point is, look at the place where maxima is attained. So look at, let's say V of x naught is where the maximum is attained. Let's call this maximum alpha. Okay, then you look at the set V bigger than equal to alpha. So by this fact, V bigger than equal to alpha should be convex, right? So alpha is the place where maximum is attained. Let's draw a convex domain. If there is one point alpha, okay, where so this is the value, alpha is the value at this maximum point. You look at V bigger than equal to alpha, it is convex. Suppose there are 2 points where the value is alpha. If there are 2 points, and by this fact that convexity is there, if there are 2 points, then this line segment joining them should also be in the level set. So V bigger than equal to alpha is convex. But if 2 points are there, the whole line between them is there. But remember, what kind of solutions are V? V are real analytic. These are level sets of a real analytic function. So if V equal to alpha, it propagates, right? You can't just have a real analytic, this curve will propagate, but then at the endpoints where it touches the boundary, V is 0. So you can't have that, right? Because you can't, V is supposed to be alpha on that whole curve. It can't be 0 at the endpoints. So that's the argument, okay? But this fact is this is non-trivial. Okay, yeah. So we have now 2 tools at hand: topological, which tells you, suppose I know it's isolated, I have a relation between the saddles and maxima, and if it's convex, then I know it's only one critical point. So this leads to a natural question: what if your boundary is not quite convex, but perhaps it changes, the convexity changes some finitely many times? So that means, so let's say that you measure curvature on the boundary. Suppose curvature changes sign some 10 times. Can you say that, can you give a bound on the number of critical points? Okay. So I think this is a hard problem. Although I believe that someone recently, I forget, there are 2 authors. One is Massimo Rossi, I think, 2 Italian authors. So they sent me a preprint recently in which it is, maybe they have solved it. I am not sure. I didn't look through it carefully, but it seems it is a hard problem. How to get a bound on critical points based on number of times curvature changes. Okay. So since I cannot solve the hard problem, I try to solve something easier. So can we look at other notions of order of omega? Okay. So for instance, changing number of times sign changes is one measure of order. So we try to give some other notion of order for this, and try to give upper bounds for this size of the critical points. Okay, so this comes to our main definition. So let me just say that, I mean, in my opinion, that this problem really requires, I mean, that some strong geometric PDE methods. So what we have done, it's not very convincing in some extent, because it's a very special set of domains. Okay, in one sense. So I will tell more about this. But okay, let's stick to topic. So what is I'm going to define a new set of domains. What are they called? They are called rational landscape. Name will be apparent in a minute. What is this domain? It is all those points Z in the plane, so that a real part of so the boundary is a subset of a set of the form where the real part of a function f equals mod z squared by 2. Okay. And what is this f? We require that f is such that the derivative of f is rational. Okay. So for instance, if you take, so when I say derivative f prime, it really means the z derivative, df dz. Okay, so for instance, if you take log mod z minus 1, if you take the derivative of this, okay, complex derivative, it will be like 1 by z minus whatever, it will be some rational function. So this is an acceptable so the set where log mod z minus 1 is mod z squared by 2, this will be by definition, this is the boundary of some RL rational landscape domain. And we associate this order of such a domain is said to be, we call it the degree of the rational function. So that measures how to what degree you have this rational function. Okay.
Koushik, can I ask you a question? This is Sivagu here.
Yeah.
So your f here is not necessarily holomorphic, is it?
Yeah, f need not be holomorphic. Like this example is valid. Log mod z minus 1 is, yeah.
Okay.
Okay. So in fact, so one can even write down. So if I want f prime to be rational, see f prime, if it is rational, you do this principle, whatever you do in basic calculus. If it's rational, you separate it out into, write it as c1 by z minus a1, blah, 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 whatever. So if f prime is this, then just very heuristically, if you integrate this, then you should get bunch of logs and a bunch of rational functions. So it is not quite holomorphic, but it is almost, except for the presence of logarithmic poles. Is that okay?
But f prime is still meromorphic. It's rational in the holomorphic sense.
Yeah, f prime is rational, but if f will be a bunch of logs and other rational functions. Yeah. Okay. So this is our rational landscape RL domain. In such domains, so you take so how to get a domain? The boundary is this. Okay. So boundary is set where real part f is mod z squared by 2. You choose and the domain, you choose to be that component where real part f bigger than mod z squared by 2. So 0 on the boundary. So if you set v to be real part f of z minus mod z squared by 2, then you choose the component. The domain is the set where v bigger than 0. Okay. So in particular, if you take like this, you see that for such a domain, for RL domain, the landscape function is immediate. It is actually the defining function of the domain itself. Okay. Because if you take the Laplacian here, you see that real part f is harmonic. So that part will vanish when you take Laplacian. So you will just have minus mod z squared by 2, and that gives you the minus 2. Right? Because Laplacian v must be minus 2 and v is 0 on boundary. Okay. So this is one reason why we consider this, because it is apparent what the landscape function is. Okay. So now, yeah, so this is the remark I made, because it satisfies both of these properties. V is 0 on the boundary and Laplacian is minus 2. So we can now give the theorem that Erik and I proved. So suppose you take a smooth rational landscape domain of order n. Okay, n is bigger than equal to 2. So remember, the order of the domain for such domain is the degree of the defining rational function. So that is f prime is the rational, whatever is degree, that is the order. Suppose you have a RL domain of order n and connectivity k. So you have k minus 1 poles. Okay. Suppose you do know that omega is not an annulus. So only that degenerate case you remove. Then in all other such domains, the number of critical points is finite. Not only is it finite, you can upper bound it by the order of this domain and the connectivity of this. So this is the connectivity, and this is the order of the rational landscape domain. Okay. So so this is one way to capture, give a bound on some notion of order in the domain. Okay. Yeah. So this is the theorem, and let me just show you some plots. Okay. So here is domain omega. This is a rational landscape domain, and in particular, I choose my f, that real part of this. This is log mod z minus e to the 2k pi I by 3. Suppose you take this level set to be a half level set, less than half, then you see that the contour plot of this, this is a domain with connectivity 4, 3 holes, right? So that's 4, connectivity 4. And the places where, so the darker colors mean that the function value is higher. Okay, so the red means that it's the highest value for the landscape function. Those are the maximum. There are 4, it forms a Y, right? This red spots form a Y. So each vertex of those Y is a maxima. And because there are 3, connectivity is 4. So if you know number of maxima, then by topological theorem that we did, S minus M is K minus 2, you compute that number of saddles is 6. So if number of maxima is 4, number of saddles is 6, then total number of critical points is 4 plus 6, 10. Okay, so that is thing. So here is another plot. So this is an example of, so this one was not simply connected, but still number of critical points was finite. You could give at most, so here is exactly 10. So here you see it's a simply connected RL domain. Here again there are 4 maxima, but this time connectivity is 1 because it's simply connected. So again you compute the number of saddles by topological lemma. You compute number of saddles is 3. So totally 7 critical points. Okay, and you might be wondering, in one sense, RL domains are plenty. Okay, because you might think, okay, I will draw some domain. Why is RL domain special? Okay, so in one way, even though it's not very useful, they are actually dense in the space of all Jordan domains with analytic boundary. So you draw some nice domain. The claim is that this is a nice proof. Of essentially a modification of Runge's theorem. So you can show that near this domain there is an RL domain. So you draw any nice domain with analytic boundary, simply connected Jordan domain. Then near it there is a RL domain. So suppose you know that, so we have proved upper bound for RL domain, right? So maybe you can think, suppose you have done it for RL domain, and using this fact, can you not do it for all simply connected domains? Okay, no, you can't, because Runge's theorem approximation and this denseness, this is only at the level of, if you want to control number of critical points. So you have V1, which is for the RL domain. This is the landscape function for RL domain, and V is the landscape function for our omega. Just because RL domain and omega are close, you cannot say the number of critical points for V1 and V. It's not that, because typically the approximation is only at the level of the level set. It's only at so you only control V1 minus V. What you need to control to get number of critical points, control of critical points, is at the level of first order. You need to control both gradient V1 and gradient V. That we don't quite have. Okay. Sorry. So this is
yeah.
You
have another 5 minutes or so.
Okay, thanks. Okay, so the space of RL domains is dense in space of Jordan domains with nice boundary. Okay, so having given one notion of order with regard to this defining rational functions and so on, here is another domain where we can associate an order. This is well known in approximation theory and numerical analysis, called quadrature domain. So very briefly, what is a quadrature domain? Okay, it's a domain where you integrate any holomorphic function. Okay, integrate f with respect to area measure on this domain. Then the value of this integral depends only on a few pre-described points. So it only depends. So integral of f depends on only the value of the function and value of the derivatives at the points Zm. So Zm are independent of f. Whatever f you give, if you integrate, they will only depend on values at and derivatives at those points. Okay, and if this happens, then we say it's a quadrature domain, and the order of this quadrature domain is the sum of those degrees. So to what power or to what highest derivative you take, those are the sums of all those derivatives. So just a simple example of a quadrature domain: unit disk. Okay, because suppose you integrate f on the unit disk. Remember, this is Cauchy's formula. This is exactly pi times f of 0. Okay, So that means that this is a quadrature domain of order 1, where we call these points Zm. These are called the nodes. Okay, so roughly the picture will look like this. So whatever, let's just draw some. So that means the value of the integral only depends on value of the function and a few derivatives at these points. So disk is a quadrature domain of order 1. So we have a bound on number of critical points on some quadrature domains, not all of them, specific quadrature domains. Okay, yeah. So let's take, for instance, suppose you have a quadrature domain, simply connected domain, which is special in the sense that in this domain, if it's simply connected, there is always a Riemann map. Suppose the Riemann map is a polynomial of degree n. Okay, then we can show that number of critical points is quadratic in n. N is the order of this polynomial, also the number of nodes for this polynomial. For this domain. Okay, so you see in RL domain, whatever order was there, notion of order, there was, yeah. So we had, it is linear. The bound is linear in n and in k, the connectivity. So if you compare that with the bound for quadrature domains, it is not quite linear. Okay, it is the bound we can prove is only quadratic in n for this special case. So what I have drawn is this Neumann Oval. Okay, it's very famous. So what it looks like, so there is a parameter. This parameter is sort of describing this sort of how sharp this point is. Okay, so the higher the parameter, it flattens out more. Okay, so you see that these are all family of Neumann ovals, and as the parameter goes up, then it becomes a convex domain. So you expect there only one critical point, but for sufficiently small parameter values, there are so this is a quadrature domain with 2 nodes which are marked here, 2 nodes, and the number of critical points. So this is explicit. We can compute the quadrature domain in so the landscape function in Neumann Oval. We know there are only 3 critical points. Okay, so it doesn't quite match with well, 2n minus 1 is what, 2 nodes, so 4 minus 1. So this bound gives at most 9. But in this specific example, we can already do better. There are at most 3. Okay. Anyway, so I think 450. Okay, I'll just finish in 1 minute. 455. So what is the idea in RL domain? So I'll just recall, in an RL domain, the landscape function was real. Oh, it's right here. Real part f minus z squared. So you look at gradient. So the gradient you compute. So it is, if you take this portion of the gradient, you will get f prime bar, and the mod z square by 2 gradient will be z. So what you have to solve is gradient v equal to 0, right? That's the set for equation for critical points. That means you have to solve f prime of z bar is equal to z. Okay, so you have to, so this is even for students in real analysis, which I will do next week. You see that this is a fixed point problem. But it's not quite a holomorphic fixed point problem. So fixed point, so you have to look at all the functions, all the points such that P of z is z, right? How do you find fixed points? Well, basic analysis tells you if you want to find fixed point, you have to iterate. Okay, so but this is not quite holomorphic iteration because f prime bar is not analytic. It is anti-analytic or anti-holomorphic. So so if you have to find a critical point, you solve anti-holomorphic fixed point problem. And this is well known. I will just mention, it's a beautiful, beautiful paper of Dima Kavinson and Neumann, Neumann, who showed that the number of such critical points, you can sort of relate this, how many fixed points are there. They showed that for a rational function of degree n, number of critical points is at most 2n minus 2. Okay, so using their result, if we combine that with our problem, you will get that number of maxima is at most 2n minus 2, and using the topological lemma, if you know number of maxima, then you also know something about number of saddles, and this gives the final bound 4n plus k minus 6. Okay. So anyway, even if you don't remember the details, the idea is rational landscape function is the landscape function is well known. It turns out to be a fixed point problem for anti-holomorphic functions. So you do some iteration in that side, and then you can bound the number of fixed points. Okay, so I will end here, but let me just state a few conjecture that as we talked initially, suppose you have simply connected domain, then there are only finitely many critical points, right? So there is a conjecture of Magnanini, who is one of the guys who has read a lot, who has done a lot on this work. So what is this conjecture? Number of critical points is at most 2m minus 1, where what is m? M is how many maxima does the distance function have? Okay, so this is his conjecture. It's sort of how many ever. So suppose you draw some domain like this, simply connected domain, and look at z, and you measure distance to the boundary. It is intuitively clear that how many ever maxima distance has, it is sort of capturing the points where the sort of convexity will change. Okay, but if there are many wiggles, it will contribute a lot to the number of maxima. So this is his conjecture, and we have our own conjecture in quadrature domains, which is that. So we had a linear bound. We usually, for a simple quadrature domain, we had 2n minus 1 squared in a simply connected quadrature domain. So we conjecture in a general, so this is based just on numerics and some one computation that we did, that it's in general, we conjecture it should be both linear in the order and in the connectivity. Okay, so these are two things, and so I will stop here.
Thank you, Koushik, for the wonderful talk. Let's thank Koushik together. So I open the floor for questions. We had quite a few. Let's have some more.
Okay, I had a question. Koushik, the quadrature domains you considered, you were looking at those where the Riemann map is a polynomial, right?
Yeah.
So I'm not sure if I'm thinking about this correct, but is there some connection to some kind of covering domain, covering business going on?
So actually, yes, in vague sense. So in general, so in general, any quadrature domain, one way to categorize it is that if it is simply connected, then the rational function will the Riemann map will always be a rational function. So this is simply connected quadrature domains are exactly those for which Riemann map is rational. But in general, yeah, you are right. There is some covering things going on here. So there is one of the guys who has done a lot on this is in TIFR Bombay, Sabyasachi Mukherjee. No, Sabyasachi. I think Sabyasachi Mukherjee, right? I don't know. Do any of you remember last name? So he has done a lot of this stuff on quasi-conformal maps and things like this, where yeah, there is a bit associated with what you mentioned. Covering stuff is associated with the general quadrature domain.
Okay, thanks. I did not know that there was a connection. So maybe I'll ask you later for a little bit more on what the connection is between being a quadrature domain and having this rational Riemann map and the covering business. Yeah,
that is one way to characterize simply connected quadrature domains. Okay, so there are some other questions in the chat. Oh yeah, Sabyasachi Mukherjee, right? Yeah. Oh, okay. Just how sharp are these bounds? So actually, so for an RL domain, so that bound is. So let me just go back. Siva asked one question for RL. Yeah, is this the So the bound is 4n plus k minus 6. We know that there are domains where this is attained. This sharp bound is there because you see that one of these here. So let me just write what is n is 3, order is 3, k is 4, and what is 4n plus k minus 6? Okay, so 12 plus 16 minus 6 is 10. So exactly 10. So these kind of domains, the bound is sharp. So in fact, we conjecture that for every k between 1 and n plus 1, there is a domain which satisfies the size of critical points is exactly 4n plus k minus 6. But so anyway, we can prove, we know that at least for some there are sharp bounds. Okay, any other questions?
So if there are no more questions, let's thank Koushik for a wonderful talk.
Thank you.
See you next week.
Yes.